called logarithms. And the idea of a logarithm is it's the inverse of an exponential function. Now you guys have been dealing with inverse functions forever. If you do 2 plus 3 equals 5, the inverse or the opposite of addition is subtraction. I could rewrite this as 5 minus 3 equals 2. If x squared equals 4, then that means the square root of 4 equals x. Now we might do that positive, negative, but at the same time, just recognizing that if I can have a function like a square, there's something that undoes that like a square root. If I can have a function like addition, there's something like subtraction that undoes that. Well, an exponential equation, 2 to the x power equals 10, I can't solve easily because 2 to I don't know what power equals 10. So there has to be something that lets me rearrange this in a form that's going to allow me to solve for x. And that something is logarithms. So we don't need logarithms for a lot of things. If it says 10 to the x power equals 1,000, then x equals 3 because 10 to the third power is 1,000. If 3 to the x power is 81, then x equals 4 because 3 to the fourth power is 81. Now 4 to the x power is 1 over 16. 16 is 4 squared, so this is like 1 over 4 squared, which means x is negative 2, because I'd want to move the 4 down to the denominator and square it. The negative is going to move it to the denominator. But if they say 10 to the x power is 47, well, I know 10 to the first power is 10, and 10 to the second power is 100, so the answer is somewhere between 1 and 2, but I don't know where. I could go to Desmos, and if I went to Desmos and I graphed y equals 10 to the x and y equals 47, I could then look and find the point of intersection, or I could use a graphing calculator to do this, and I could find that x is about 1.67. So in this case, if I do that, I get 1.67. The problem is I don't always have those tools handy, and I need to, again, find a way to incorporate these into other functions that I can use. So instead, we need to find out what that inverse function is, and it's called a logarithm. Notice here that 10 is the base, 10 is the base, x is the exponent, equals 47. This is called a base 10 logarithm. So I would read this as log base 10, and if I read it correctly, it's going to help me rearrange this equation. I know in this exponential equation 10 is the base, so if I read this as log base, the 10 has to go there. The other part isn't as easy to see, but notice you're never going to see this down here. So the exponent goes on the other side of the equation. So log base 10 of 47 equals x. Usually you don't actually show a base of 10. If there's a logarithm like this with no base showing, it is a base 10 logarithm. And if you look at your calculator, there is a button that is a log, or it might be in capital letters, logarithm button to use. That is a base 10 logarithm. So I can go to my calculator and punch in the base 10 log, so just using the log button, of 47 equals, and I get x equals to 3 decimal places 1.672. Again, I expected it to be that because I got 1.67 from Desmos, so it's got to be pretty close. This just was, I rounded differently. So I can go, and anywhere it just says log with no base showing, it's a base 10, I can use that button on my calculator. Now I know 10 to the something close to 1.67 would equal 52. This ends up being, and it says to 4 decimal places, so x equals 1.7160. I'm going to skip this and come back. I can use the log button here. X equals 4.0904, which means 10 to the 4.0904 power is roughly equal to 12,314. Now there's another button on your calculator that's either that, or they might write it in capitals. That is also a logarithm. If you see log, it means it's a base 10 logarithm. If you see natural log, it's a base e logarithm, where e is Euler's number, which is 2.71828, blah, 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 blah. So if it gives me a natural log, I'm going to use the natural log button on my calculator. E to the what power equals 21? Well, it's to the 3.0445 power. e to the what power equals 0.4567? Well, it's to the negative 0.7837 power rounded to 4 decimal places. So make sure you've practiced punching these into your calculator to get the correct answer. The problem we run into is when I don't have a base 10 or a base e logarithm, because there's no button on most calculators that allows me to do that. Now I understand some of your calculators allow you to put whatever button, whatever base you want to in, but I still expect to see the work on these because not every calculator you pick up will allow you to do that. So show me this work. What happens is, if I get this, I can convert it to, so the log base 5 of 12, I can't plug that in because it's a base 5 logarithm, but it's the same thing as the base 10 logarithm of 12 divided by the base 10 logarithm of 5. Now I know which one to put in the numerator. It's the one that's already kind of above the other one, and the other one goes in the denominator. So I'm going to put the log, and most of your calculators put log, they open a parenthesis, put the 12 in, close the parenthesis before you divide it by the log of 5. You don't have to close this last parenthesis because you're not doing anything after it. So in this case, 5 to what power would be 12? Well, it's somewhere between 1 and 2 because 5 to the first power is 5, 5 to the second power is 25. So it ends up being 1.5440. 5 to the 1.5440 power, roughly, equals 12. So the first thing I'm going to do is to rewrite this. This is the same thing as the base 10 log of 126 divided by the base 10 log of 4. Plug that in my calculator. 4 to what power is 126? Is 3.4886. This is going to be the log of 32 divided by the log of 12. And what we're doing is called the change of base. We're changing this from a base 12 logarithm to base 10 logarithms that I can work with. So 12 to what power is 32? Well, that's to the 1.3947 power. 42 to what power is 15,000? Well, I'm going to take the log of 15,000 divided by the log of 42, and 42 to the 2.5727 power, rounded to 4 decimal places, is going to be my answer. 13 to what power is 2,516? Well, to find that answer, I'm going to take the base 10 logarithm of 2516 and divide it by the base 10 logarithm of 13. So 13 to the 3.0529 power is 2,516.